sitting between us now and the coffee break, there's a few things I'd like to discuss today. So the first thing is to go over some of our current approaches to storing operator state in popular data streaming platforms that we all know and love. Secondly, I'd like to introduce both RocksDB and FASTER. Just to get an idea, how many people are familiar with RocksDB? Like, a lot? Okay, great. Never talk to people who know more about your area than you're presenting. And how many people know about FASTER? Okay, a lot less. That's good for me. What I'd like to do after introducing both of RocksDB and FASTER is kind of compare their suitability for different streaming workloads. Quite what that means will make more sense later on, hopefully. And then finally conclude by explaining what that means for Flink. So if we go first for current approaches to storing operator state. The topic of state management is massive. I mean, over these next 2 days, there's lots of different talks with state management somewhere in the abstract. What I mean here when I'm talking with state is specifically about where do we store state. So in the first case, when we start up a Dataflow program, the obvious place to store state is on the heap, within the process's memory. So this is really good for things like debugging, fast iteration of our new Dataflow programs. But at some point, we realized that we really need to step it up. And we actually have to start storing more state than we have available memory on a single machine. And then what we might do is actually start storing it in a file, possibly on a remote file system. Using a remote file system gives us advantages over using it on a single machine for some of the kind of obvious reasons of being able to rely on fault tolerance of the remote file system like HDFS or something. But at some point, our file abstraction is not really quite what we need for our data store for stream processing. So we move on and we decide to use a dedicated data store. Now this data store, we either have two options really. We can either embed it in the process, so this is what we're doing with RocksDB, or we have a remotely accessed data store, something like Cassandra or HBase. So why would we use a dedicated data store? One of the main reasons, I think, is because we all love abstractions. A data store often provides us with a simple abstraction, something like a key value model, and that kind of moves us away from a physical model. By physical, I don't really mean looking too much at the low-level implementation details, but the idea of how state is being arranged on hard drives and things. Secondly, it allows us to outsource responsibility for fault tolerance. Most data stores have some form of fault tolerance. This includes the ones I'm talking about today, both RocksDB and FASTER. It allows multiple processes to share state, especially if we have something like a remote data store. We can have multiple processes on multiple machines accessing the same shared state. However, I argue that this may not be actually that useful, and I come back to this point later on. Finally, it really allows us to separate responsibilities. We let the data store get on with doing its optimizations. It's looking after how to store our state and make it available to us. We, as Dataflow programmers, we just get on with writing the actual code and solving the problem that we care about. So I said there's really two options with using a dedicated data store, whether to store remotely or store locally. And both options are equally valid, really. If we look here, one's using remote data stores. We have Apache Storm with the Trident API relying on Cassandra. And then we also have Google Cloud Dataflow, which is then using Bigtable. Apache Samza, Apache Flink, both very popular stream processing systems, they actually choose to store their state locally within the process operating the data flow. So when choosing a local data store, if I'm a Samza, Flink, or indeed Apache Kafka, there's only really one option that I've chosen over the last few years, and that's been RocksDB. So RocksDB is a very, very popular embedded key value store. It is really the de facto choice for choosing to store state within a process. And what I'd like to do throughout the rest of the presentation is maybe challenge that assumption that RocksDB should be the go-to for embedded data store. So RocksDB. To give an overview of RocksDB, then it started life at Google as LevelDB and then was forked off. For people who don't know, it's an embedded key value store for arbitrary byte streams. That means basically within a single RocksDB instance, I can store whatever state I like as long as I serialize it down to a byte array. It provides the basic operations that you might expect, sort of inserts, deletions, gets, but also more advanced operations such as merging multiple values together and also performing applying compaction filters when deciding on values to retain and things. It allows very efficient range scans using prefix Bloom filters, and the architecture of RocksDB is based on a log-structured merge tree, an LSM tree. I'm going to give now a kind of a brief description of how an LSM tree works to try and motivate an understanding of the implications of FASTER's structure. So when writing key-value pairs, we start by appending them to a log. So this top here, this is called a mem table in RocksDB. It's just an append-only structure that we have residing in memory. At some point, this structure becomes full, and so we mark it as immutable, and we spawn a new one. This is now where we're going to start appending onto our new key-value pairs. This process kind of continues until at some point, we run out of space, and we have to perform a compaction. So a compaction is taking multiple mem tables from above, in this example 2 for simplicity, and it's effectively performing a merge sort. So it's combining these two higher level mem tables together to give us the compacted view. Now, a nice feature of this merge sort is that the result is that these two are both sorted. This kind of gives us a clue as to why our range scans are so efficient, because we have all the data here sorted in this level. The process kind of continues, and we can have more compactions. As we do more operations at the top level, more appends, we can trigger further compactions further down in the tree. It's it's a recursive process, this happening. For simplicity, I've just shown it happening directly straight after, but in reality, we would be able to configure how often these things happen. So in RocksDB, we have this top-level mem table, as I said. These reside in memory. And then we have all these are called SS tables, the ones which we're actually storing on the disk. RocksDB, if you work with RocksDB, you know, has 1 million configuration options. We can control the size of these different things, how many of them exist before we start doing compactions and things. We can also perform manual compactions of our LSM tree. But I hope this has given a kind of rough intuition for the design of RocksDB. If we look at its full architecture now, though, we see, okay, the simplest thing is on disk. We have these SST files where we're storing these lower levels of the LSM tree. And then in memory, we have both our mutable and immutable mem tables. So remember, the mutable one is the one we're currently writing to, and the immutable one is the one which we've closed, but we're just waiting to be able to compact and flush to disk. We then have a block cache for when we're accessing blocks out of our SST files. We have a manifest file, which is storing metadata about our blocks. And we have a block index to be able to easily find blocks within SST files. So having seen the design and the architecture of RocksDB, I think it's important to look at what that kind of means in terms of using RocksDB for storing state. One consequence is a very high write throughput. So I said that on this mem table, we just have this append-only structure. So that means we can work on it really quickly. It's a really fast kind of concurrent action just to append onto these mem tables. Our compactions that we do can happen asynchronously. In our diagram earlier, I kind of showed that all 4 of the mem tables filled up, and then we did this synchronous compaction. In the real world, it's not like that. Maybe 3 out of my 4 ones are filled up, and then I do a background compaction while still being able to append to the 4th open mem table. Read requests may access multiple levels of the tree. So my data becomes replicated in multiple different levels of the tree, and it has to look in different levels to find the latest data. This is called read amplification, and amplification is this kind of measure of how many operations do I have to do compared to my one desired operation. So if I have to if I want to write something, if I have to write it 3 times, then I have a write amplification of 3. And we find with RocksDB that we have quite a high factor of read amplification. And the final thing is to say, because we have this append-only structure, when we want to make a change, we have to read the old change, copy it to the end of the log that we're appending to with the updated value. This is an expensive operation to perform. So moving now on to FASTER. I'm going to do the same thing, go through like an overview of FASTER, the design, its implications, and everything. So FASTER is an embedded key value store, just as we had before, but now for arbitrary data types. So I go say that again. It's for arbitrary data types. It's not as before, where we had to serialize our values down to a byte array. We're actually now able to encode in our design of a FASTER instance the actual representation of our data. We decide how it gets represented on FASTER's log, which allows us to do some kind of cleverer things and avoid the need for serializing. FASTER exploits the strong temporal locality in streaming workloads. What does that mean? It means that in streaming workloads, we typically find that a subset of our total state is very frequently accessed. So we call this the hot state. What FASTER does is it separates its entire state that it's storing into an in-memory hot and on-disk cold set, so that state that we're accessing frequently is available in memory, and state that we access less often is going to be stored on disk, waiting for us when we do actually need it. FASTER is much simpler in terms of operations that support it. It supports point reads, blind upserts, and a read, modify, write operations. These operations are all user-defined functions. So I said that we're storing arbitrary data types. What FASTER does is it pushes the responsibility onto the application developer to decide how do you want to implement an upsert, how do you want to implement a read, modify, write operation. For example, if I have my data type is a pair of sum and count, if I'm doing an average or something like this, then I want my read, modify, write to be adding values onto both of those fields. And if, say, my data type is a list of ints, then I want my read, modify, write maybe to be an enqueue on the back or push onto the front. This is responsibility of me as the application developer to decide how to implement these operations. And the structure of FASTER is a HybridLog, which supports in-place updates. So here's FASTER's design. This is the HybridLog, which we can think of from a logical level as a contiguous space, which is then divided into a portion which is stored on disk and a portion which is stored in memory. So starting then from left to right, makes sense. On disk, we have the elements which are part of this cold set. So these are elements which would have begun life at the end here on the right as new records at the end of the mutable section. And because they've not been accessed, they've kind of ended up falling off the end of this logical address space as the stable period has overtaken it, has become resident on disk. We then have, at the end of this in-memory period, between on disk and mutable, this read-only part. Now, this read-only part is actually pretty clever because it acts as a second chance cache. And what that does is it reduces the chance that a hot item is going to be spilled to disk. Because as I said, this stable period, it kind of grows, and maybe it's reaching a hot item, and it gets actually put in this read-only section. If it gets accessed again, it gets moved to the front, to the end of the mutable section, and it won't be evicted onto the disk. And then finally, we have this mutable portion. So this mutable portion is where we have in-place updates supported. That means it's super quick to make a change. We don't have to do this expensive read, copy, update operation that we had to do with either RocksDB or when we access something from the stable period or the read-only period. Period, I mean like section, the read-only section or something. So the entire architecture is here summarized on one slide with only two things. And I really like this about FASTER. It's a really simple architecture. We have this HybridLog, which we can imagine as developers as just a contiguous logical address space, and then a hash index. The hash index resides in memory and is actually very cache-optimized. So there's lots of care taken in the code, in the implementation, to make sure that, for example, like a hash bucket entry is just one cache line, regardless of like the architecture being used. So it's considerably simpler than RocksDB, a lot fewer configuration options. Obviously, there's arguments whether that's good or that's bad. For me, I think it's really good as a developer just to be able to spawn up a FASTER instance, provide a size for a hash index, a size for the HybridLog, and go, as opposed to spending hours and hours tweaking a RocksDB configuration. So the design implications then of having this HybridLog and this hash index in the architecture. It has a very high read and write throughput, and this is especially true when we're accessing the hot set. State which is accessed often is just going to be available in memory, and it's almost as if we were going back to that original place of storing our state just on the application heap. Obviously, if we have to access it from disk, it's more expensive because we have to do a retrieval, but then in the general case, in our hot case, it's very cheap. FASTER's internal design is lock-free, and this allows very scalable, multi-threaded access. FASTER supports a kind of a publish-subscribe mechanism so that threads can dynamically come and take part in the operation, in its internal operations, all without having to take locks and things, which is quite in contrast to RocksDB, where there's quite a lot of locking, controlling a lot of operations. FASTER's in-place updates reduce write amplification massively. If I'm making frequent updates to a hot set, maybe I'm, I don't know, counting the number of tweets made by Beyonce in the last day, you know, this is only taking me up one space in the whole HybridLog. I'm not having to perform any kind of read copy update and really increasing write amplification in the way that RocksDB would then do so. Finally, though, scans are expensive. If I want to do a scan, I basically have to start at the beginning of the log and work all the way to the end to find all the different things which are in it. This is not very good, as we'll see later, for doing something like windowing in a stream processing system. Oh, and actually, that wasn't my final point. A single FASTER instance can only be used for one key value type. So there's kind of a subtlety in saying it so quickly that in the past, when we used RocksDB, we said, OK, here is our RocksDB. This is our one database. You use it for the whole of your stream processing. You can store whatever it is you like in there. Now that we have to tailor it to one data model, we can only use one instance per state primitive, basically, per key value type. So I think that then needs explanation of what that means for using FASTER for storing operator state. If in the first case, then, we like our way of doing RocksDB, that we have for RocksDB this very generic mechanism to be able to store state however we like, and we want to move towards doing that for FASTER, then we have to look at how we actually represent our keys and our values. And it goes back again to serialization, the same as we did with RocksDB, is we have to represent our keys and our values in some kind of byte buffer. So if we want to make a generic key value type, then there's some things we need besides just the actual buffer that we're using to store the key or store the value. Clearly, we need the size of the buffer. We use the size then to make sure that we're reading out the correct amount from the buffer. But for our value, we need a couple of extra pieces of information which have kind of an impact on the size of the value class entirely and its scalability. Firstly, this value length. We support in-place updates in this generic approach, but an in-place update doesn't necessarily mean that our new value is going to be the same size. It might be smaller. So if our new value is smaller, we can still store it in the same byte buffer. We still have 20 bytes reserved or something. Our new value is 12 bytes. We just store it in there and just store the length. We say that there's only 12 bytes of kind of usable space. On the flip side, by the way, if we wanted to make it larger, if we have a 20 bytes reserved, we would need a 30-byte thing. Then we have to do an RCU. We have to make a new value because we need more space. And then the last thing we have in this value type is a atomic genlock. So I said a couple of slides earlier that FASTER was really nice and lock-free, super scalable. But the reality is, if we want to store just like an arbitrary byte array, then we have to protect against multiple different, multiple threads changing a value at the same time. So we put a lock in there, and writers have to acquire the lock before they're able to make a change. So this design, by the way, this way of having an arbitrary key value is what we do in FASTER RS. So FASTER RS, co-designed by myself and Max Meldrum, who'll be part of giving the talk later, we have created this very generic wrapper for FASTER to be able to store any serializable state. And I have a link at the end to that if you'd like to check it out. But my, question is all this overhead for arbitrary state necessary? So we are allowed to store arbitrary state in RocksDB. We've now come up with a way of doing it for FASTER, but is this necessary? And I think we make two observations. The first one is that streaming jobs are data parallel. That is that one worker is probably going to be responsible for the subset of the input that no other worker then has to worry about at any time during its processing. So as a result, do we need all these locks and things? If I'm the only person who's going to edit the data for, the number of tweets by Beyonce, then I don't need to acquire a lock every time I try to modify it because nobody else is going to try and modify it under my nose. And the second point that I make is that we know the types of state that we're using in our stream processing in advance. We're not being super dynamic, we're just receiving new data types and then having to store them in the way that RocksDB is kind of designed for. We know what we're going to be storing in our stream processing job, so let's optimize our system to be able to store that kind of data. And we can start looking now at the advantages of using a hand-tuned store. So in this experiment, what we've done is we've implemented the YCSB benchmark, which is from Yahoo. It basically is a store key value of integers to integers. And we process a sequence of transactions just to store and read integers from the database. And we've done this using both the hand-tuned implementation, so this is one which knows that it's going to be storing integers, so it's able to just write the integers directly, and then one which is generic, the FASTER RS that we've seen earlier, which has to do this serialization, acquiring a lock, storing the extra information, such as the size and the length. And in our general case of a 50-50 read-write workload, we can actually see there's a 1.6x speed up by using a hand-tuned store rather than our generic store. So to get to the crux of the issue now is to kind of compare FASTER and RocksDB in a streaming workload setting. For this benchmarking, what we do is we implement a range of NEXMark queries. So NEXMark is a streaming benchmark designed to replicate traditional relational operators, things like maps, joins, filters, aggregations, and it models an online auction service. So what we have is we have streams of bids, auctions, people making bids, people making auctions, and different queries replicating relational operators. We run these on a EC2 instance, which is equipped with an SSD, because our experiments will be based on larger than memory workloads. For our integration, we do an integration between FASTER RS, so the Rust wrapper, and then Timely Dataflow. So Timely Dataflow is a stream processing system based on the NIAD Dataflow model. I don't want to talk about it too much because it fundamentally works the same way as something like Flink, apart from we can have cyclic data flows. But everything we're really designed to be data parallel. We take a logical data flow graph, and it's just a runtime for working out how to execute it. So the first query we're going to look at is NEXMark query 3. Queries 1 and 2 don't contain state, so if I seem strange, I just jump to 3. It's because of that. Query 3 then is an incremental join between two different streams, an auctions and a person stream. And the state that we're maintaining in this query is we're maintaining these auctions and these persons relations, so that when we receive an auction or a person from the stream, we're able to look it up in the corresponding relation and output the results of our match. It's an incremental join, which means that it continually accumulates state throughout processing. So I put this graph up. That probably needs a little bit of explaining before jumping straight into it. What we do to collect these results is we measure the per record latency when we're processing tuples, and we calculate the CCDF, which is the complementary cumulative distributive function or something like that. And so the simpler way to read it, instead of reading the numbers on the left, these 10 to the minus whatever, is to think of these in terms of a P90 latency, a P99 latency, P999 as we go on. So what the graph shows us is that mostly the performance is not very different actually between FASTER and RocksDB until we reach around a P993 or so, and then we start seeing this astronomical difference. So we start seeing RocksDB actually having basically 2 orders of magnitude latency being worse compared to using FASTER. And I mean, that's really quite terrible. Then we're having records being processed in basically over a second by using RocksDB. So the next experiment we do is with query 4 of NEXMark. NEXMark query 4 is reporting the average closing price of auctions grouped by their category. So the state we store for this is we're storing the sum and the count for each category, and we're also recording the bids for each auction. Once again, when we look at the graph, we can look and see that there's similar performance. In fact, for some, it looks like RocksDB is beating FASTER up until this like kind of P95, sorry. And then we see an increase for RocksDB. Here it's only about an order of magnitude difference, but still RocksDB is losing considerably compared to FASTER. I want to go now on to query 5. Query 5 now is a bit different because now we have windowing. So here we have a sliding window, which is reporting the auction with the most number of bids. And the state it's maintaining is a count for each auction, and then we're applying our windowing logic. If we look then at the graph, it's much closer in this one, but still we see FASTER outperforming RocksDB. And at this point, it begins to look a little bit like I'm just giving a sales pitch for FASTER, and that this isn't very interesting. FASTER is just better for everything, which we don't believe is the case. So this brings us on now to some research that we're now doing at ETH, which is to look and see what happens if we change our window implementation. Perhaps we can actually elicit better performance from RocksDB, potentially better than FASTER, by changing the way in which we do windowing. So these next couple of slides, it's early results from ongoing work. So bear with us a little bit on it. Happy to talk more in the break about how we are deriving these kind of results and things. But if we change our windowing logic so that what we do in terms of applying a window operator is we buffer records in state ordered by their timestamp. And then when a window triggers, we retrieve the records belonging to the window by using a range scan. So we go through from the start of the window, and then we search for all our records in the window based on timestamp, and then apply our evaluation function. In this case, I think we're just counting the number of records. So what this maybe not so clearly shows, let me say first what it is that we're comparing here in terms of the colors. That might be easier. So the green and the yellow colors we want to compare. So that's green is like RocksDB, and yellow, green and yellow are both RocksDB, sorry, and then purple and blue are both FASTER. So what this shows us here is that RocksDB is beating FASTER. And there's actually 2 different experiments here, because what we've done is varied the slide on the sliding window. So if we look at the FASTER, we look at the purple is with a 2-second slide, and then with the blue is with a 50-second slide, and then for the RocksDB, the green is it's the same respectively. What we can see here for RocksDB is we actually have a similar performance regardless of the amount of slide that we have. So whether we have a 2-second slide or a 50-second slide, we basically have the same performance because it's a range scan. So what I'm doing is I'm just going to the beginning of my window and just doing like this scan through this nice sorted list and being able to just pick up records. And it's kind of then agnostic whether I'm searching for 2 seconds or 50 seconds. They're laid out after each other contiguously, so it's not a big performance difference. FASTER, on the other hand, is different. With FASTER, we can see that the performance degrades as we increase the amount of slide. This is because we're having to do basically 50 lookups as opposed to 2 lookups if we have a 2-second compared to a 50-second one. And that's why we see FASTER doing worse. And this suggests then that for this kind of implementation of a window, we do better by sticking with good old RocksDB rather than moving on to new kid on the block, FASTER. But now let's look at a different way of doing windowing. And I think this way of doing it is the Flink approach. And what we do is we assign window IDs when we're doing our kind of windowing operator, and we store state keyed on these window IDs. Then when a window expires, we can fetch the window content by doing a lookup using the window ID. For this, it looks like we have FASTER performing better. So FASTER is the purple and the blue line again, and then RocksDB, FASTER is purple and green, and then RocksDB is the blue and the yellow. But fundamentally, RocksDB is further to the right, which is bad compared to FASTER. We see here there's two different types of window based on the amount of slide. So we have this small sliding window of 5 seconds, which gives us a small performance difference. And then with a tumbling window where we have this 100-second slide, basically, we have a much bigger difference between the two results. And so the reason for this is because we're going back to what we saw previously with FASTER outperforming RocksDB in terms of it being better for this kind of just lookup, get, put kind of operations. So what does this mean for Flink? We're at a Flink conference. Disclaimer here, we were really hoping to have kind of an early stages integration between Flink and RocksDB to kind of show off now, see how that worked, especially with the windowing logic. Fortunately, we haven't managed to achieve that just yet. It's something we can definitely leave for the community. We have the early stage, we have an integration with Rust, which is what you could then use as a basis to then do an implementation with Java. We just didn't really have the JNI experience to try and push through it in advance of this talk. So I think the lesson that we learned and could go forward then for Flink is that when it comes to choosing a state backend, the easiest one to integrate is definitely not going to be the best one. We've become quite settled using RocksDB, but it's definitely time to consider other options to be able to have low latency data stores. I definitely say that we've shown generic data stores provide great flexibility, but by actually looking at what our state access patterns are and how we're actually using our data and how it's represented, we can actually look at using different state backends which might be more suited. And also, like a death in a way to the monolithic backend. This is going to become really important when using FASTER, because with FASTER we've got this kind of caching functionality. And if you imagine that we would use one monolithic backend for an entire job, then we're going to start seeing different operators kicking another operator's state out the HybridLog just because of sharing the one backend. Also, with FASTER, if we're only allowed one key value type per instance, then as we're going to store different types of data, we're going to need different backends anyway, different instances. So I have a little bit of a proposal to make, which is that when we do eventually come to integrating FASTER with Flink, we create a suite of hand-tuned FASTER instances for storing common data types. So when a Dataflow developer knows that what they want to store is a sum and a count, they can go and pick up this ready on-the-shelf FASTER instance, which is optimized for storing pairs of integers. Similarly, for things like lists of primitives, we can always have some kind of community contribution of different hand-tuned FASTER instances, which would be really good for storing state. And the proposal is also to do the work that we're ongoing at the moment, which is to look at the different ways in which state is being used, not just window operators like I put here, but also generally when people are doing stream processing, what are the state access patterns and what state backends could suit that. So some open questions to lead on for more research for anybody who's interested is how do we accommodate fault tolerance in all this? So FASTER has its own way of doing fault tolerance. RocksDB has its own way of doing fault tolerance. Say we did an integration with like Cassandra or something. How do we combine all these different fault tolerance mechanisms together? That's an open question. How do these different ones compare for something like queryable state, which is very much a Flink thing? It's not something we have in Timely Dataflow, so we've not got any research on that. And really, what other key value stores would it make sense to kind of compose with FASTER and RocksDB? So with that, I have to put the obligatory "we're hiring" slide at the end. This is the result of a lot of work that I did during my master's thesis at ETH Zurich. They're doing lots more cool work in the Streamon group, lots of interesting research in data stream processing systems. Feel free to talk to myself or Vasya, who was just on before me, about what's going on there. I now work at Monzo in London. If you've heard of Monzo and are interested in opportunities there, feel free to come and talk to me. I don't work with Flink, so maybe that's a shout into the void. But I'd like to leave with some resources. We have here links to the original FASTER repo, our implementation, Max and I, of doing it in Rust. All the queries using NEXMark here are available on my GitHub. And then finally, there's a link to my master's thesis, which I did at ETH, which has loads more information, loads more graphs and description of getting the best out of FASTER, I think. So with that, we're happy to take any questions.
One of the advantages of using an append-only log is that you don't delete from the middle. The impression I got is that the FASTER log does delete from the middle of the log. Is that correct?
So FASTER's way of doing it is to apply like a tombstone header. And then when we eventually spill it to disk, we can inspect it and see if that header is there, then we don't spill it to disk.
So if you move something to the front of the log, meaning that it's fresh or hot, then you apply tombstone in the back and you copy it to the front?
No, because if we're then doing, say, a lookup later on, then our hash index is just pointing to that most recent entry. If I do a delete of something and I never reinsert it or anything, I will have at the deletion point taken it out of the hash index as well, so it won't be found. So this contiguous logical address space kind of becomes restored once I would, in theory, have spilled it to disk, but I just don't do that.
And I'm guessing you spill the oldest ones, which are the most at the left,
yeah, of
logically.
The graph. Yeah, of the diagram.
Okay, thank you.
Let's thank the speaker once again.